So a quick introduction from my side. I'm Sebastian Keller, and I work at CSCS as a computational scientist. And one of my projects dealt with molecular dynamics with GROMACS. And so I'm going to tell you a little story of what we did there. So that's ongoing work actually at CSCS together with KTH Stockholm. And one issue that we tackled there was the modernization of the bonded molecular forces in GROMACS. And so the current implementation there is in pure C essentially. And we then updated that to C++17. We employed techniques like strong typing, TypeLists, tuples, and Sphene. And then how that changed the code is the topic of the story I'm going to tell you. So first, perhaps a quick introduction, what classical molecular dynamics is and what bonded forces are in particular. So classical molecular dynamics deals with a simulation, so the time evolution of atomic systems according to Newtonian force law. And so it's not quantum mechanics, it's actually classical force laws. And this is commonly being applied, for instance, to proteins, enzymes. So that's the slide that I was missing before. So as I was saying, the current implementation is in C, and we've updated it to C++17. And these three items here are what we use to update it. And then, yeah, just to quickly introduce what molecular dynamics is all about. Yeah, I was saying that it's really classical force law, so it's not quantum mechanical. So that's one thing to keep in mind. But this is nevertheless routinely being applied to proteins, enzymes, lipids, and membranes. You can also use it for drug docking. And for instance, most recently, there's ongoing research, for instance, to simulate the COVID-19 virus. And so in particular, bonded forces in molecule, there's perhaps three main categories where you can look at. So for instance, there's bonds, that's involving two atoms, angles involves three, and then dihedral interactions involve four atoms. And so when you look at this example molecule here on the right, so the red line here is where a bonded force would act, and then here the angle is between those three atoms here. So that kind of gives you the force that's according to how much the angle deviates from its resting position. And then you also have dihedral interactions here. In this case, the four atoms involved here, and that makes sure that here the ring stays planar. And just from a physics point of view, it's actually really simple. For instance, one possible type of bonds is just to use a harmonic spring. So the force that you have on the two atoms involved would just depend or would just be described by the simple force law, where the force driving the atoms back to the resting position is just proportional to the displacement. And there's two parameters. So there's a spring constant, and there's the equilibrium distance. And so this benzene system here actually has two different kinds of bonds. So there's the carbon-carbon bond and the carbon-hydrogen bond. And You can model either of these bonds with a harmonic spring and then just use different parameters. But here it's really important to point out that harmonic springs are not the only possibility. You can also have different functional forms. For instance, a cubic force law or a linear potential energy laws. And so if you do have a different functional form, then we say it's actually a different interaction type and not just different parameters. And so here, this is an overview of all the bonded interactions that you can have. First, you get the main categories according to how many atoms are involved in your interaction. And then for each category, actually, I can have different functional forms. And just here to give an example, GROMACS implements 30 different of these interaction types. And then there's a series of bond types, a series of angles, and also some more dihedrals. And how do you really do that in practice? And the answer is that you need two tables. You first number your atoms as is shown here on the left, and then you need a table for the parameters where you store the spring constants and the equilibrium distances for your unique bonds. And then you need an index table that keeps track of actually each interaction that you have in your molecule. So for instance, here, I mean, the index table would contain much more than just these two entries, but just as an example, here the bonds between atom 7 and 9 would result in an entry like this. So you have an index for the two atoms, and then you need another index for the parameter to look up the spring constant and equilibrium distance. And so similar actually between atom 7 and 8. So 7 and 8 are your two indices, but then you need a different parameter index because the spring constant would be different. So now I'll just quickly give you an overview of how that was traditionally done in just a pure C implementation. And the first thing here to point out is that GROMACS uses a union type to put all these bond interaction types into a single union. So there's this union TI params, and then regardless of whether it's a harmonic bond, an angle, or a dihedral interaction or something completely different, it's all in this one single union. And so that, for instance, already means that each instance of this TI params actually uses as much space as the biggest interaction that you have in your system. And now it's actually pretty simple to fully define the whole interaction table. And in GROMACS, it looks like this. The parameter table is actually just a single vector that has all those parameters. And so since it's a union, it's all the same types. So that information, what particular type it was at here in this format, did get discarded. And so it's flattened over all the parameter types. And then for each of your interaction type that your code, in this case that GROMACS can handle, you have one of these tables with the interaction indices. And so you can imagine that you have 30 tables that contain the indices of the atoms that describe you where the bonds or the angles are. And once you do have this interaction definition, basically the only thing you need in addition to compute forces is the coordinates. So once you know where all your atoms are and where the interactions are, you can just write a loop over all your interaction types. And the way that this has been handled is to just retrieve a pointer from a function table, and then that function knows how to deal, for instance, with harmonic bonds. And then you compute all forces for harmonic bonds. And so the way that this looks like in simplified terms, so you need the parameters from the parameter table, the indices, the coordinates as input and forces as output. And so you make a loop over all the harmonic bonds. You look up what the indices are, look up the parameters, and then you load the coordinates, and then you can apply Hooke's law for the force, and then you store back the result force. And the issue here really with this approach is that here the highlighted red part is really the only part of the code that's unique to harmonic bonds. All of the other statements here, for instance, loading of indices and parameters, loading coordinates, storing back forces, that's actually shared between all the different bond types that your code can handle. And so that's code duplication, which we don't like. And another issue is that it's actually not so extensible. So if you want to add a new bond type, there's no single place where you just can add that new interaction definition. You first re-implement everything, the whole handling of interactions from scratch again, and then you need to change multiple data structures. And so that's another issue that we want to improve on while moving to C++. And so let's actually look how that could be addressed with C++. So the first thing to do there is to actually say, well, instead of just putting all the interaction types in a union and throwing that type information away, let's actually implement that as proper C++ types such that we can leverage all of the compiler technology with templates and so on to generate code for us. So for each of the 30 interaction types, we're going to have a separate class or struct. And then second, there's actually now a way that we can also make the parameter and index tables type aware. So instead of just storing the unions in the parameter table, we actually store a separate table for each interaction type. And then now here, if we want to store the index, there's already an observation that now the number of indices that you need depends on the category of your interaction type. So for angles, this is actually a vector of 3 indices. And if there's an angle, you need 1 additional index. And so there's already one little meta function that we can write for that. So we need to encode somewhere that if the interaction actually has n centers, then we need this to be an STT array of integers of length n+1. And we also ideally want to store that information only once, how many of these interaction centers there are involved for a given type. So, and one way that you can do this in C++ is to just list your concrete types, say harmonic bonds, quadratic bonds, angles, and dihedrals, and so on. You add them to a type list, which can, in its most basic form, just be this empty template with a variadic number of template parameters. So this actually works. That's not a simplification here. And yeah, now we can use tricks like Sphene to actually make this work, that we can say end center, and then we instantiate this with harmonic bond or harmonic angle, and then it would actually evaluate at compile time to the number of centers involved in this interaction. And so there's just one little extra trait that I need here, and that's this contains meta function. And so that one evaluates to true if A is contained in B, and B is one of those type lists. And so how is this really evaluated? So if you instantiate here end center with harmonic bond, there's a default parameter. And so end center of harmonic bond is really harmonic bond, comma, void. But then you also have the first specialization here, where so contains harmonic bond to center types evaluates to true. And so the enable if t of true evaluates to void. And so the first specialization also produces end center instantiated with harmonic bond, comma, void. And so the specialization is more specialized, and that's what's getting selected. And therefore, end center harmonic bond is an integral constant with a value of 2. And likewise for angles. So we just need a specialization for each category. So thanks to this little trait, the parameter and index table will have the correct number of indices for every interaction. So if we instantiate our table, the parameter index table with harmonic bond, then this will correctly have 3 indices or 4 indices for an harmonic angle. And now if we actually wanted to store that for all the types that we support in our code, we could, for instance, just put all these parameter index tables into a tuple. But then we've already listed in those type lists for the categories what types that we support in our code. And one thing that we don't want to do in C++ is repeat ourselves. So remember, there's 30 of them. I don't want to, have to keep track of this tuple type. Instead, it would be much nicer if I could just generate the tuple type from the type lists I already have. And we can do that indeed if we use some more meta functions that operate on type lists. So, for instance, if I can say that I want to combine existing type lists and make another type list, then I could use the 2, 3, and 4 center types to just fuse them into one list that has all the types. And then next, I can define a function map. And so, oops. So map takes the first parameter and takes a list as a second parameter, and then makes a new list where T is instantiated with all the elements that were in the list. So if I do map parameter index table to interaction type, then I get actually a list of parameter index tables instantiated with all the types that I have in my code. And then I can define another operation, reduce, which just pulls in all the parameters of the list and uses them to instantiate T. So if I say reduce T of some type list, then I will get T instantiated with all the items in there. And if I use that, or if I apply that for the tuple here, this is exactly what I wanted just 2 slides back. Namely, I wanted a tuple that contains the parameter index table for all my interaction types. And I don't really have time to go through the details of how all those type traits work and operations on TypeLists, but you can look that up. So it's actually pretty minimal implementation. So if you want to see how that works, also including the contains trait that I didn't tell you how it really works, you can look up the test and the implementation. It's only one file, so it's pretty minimal. And if you're interested in that, you can see how that works. So moving on. So now I'm able in C++ to store all the information that I need in a type-aware fashion. And now the question is, does that actually help me to avoid all that code duplication that I mentioned in the beginning? And so let's see. This is the function that calculates the force due to a single interaction. So a single bond or a single angle and so on. And now I can actually write or implement just one function to handle all the bonds. Because I'm using different types now, I have the option to just overload, use classical overload resolution to distinguish between the number of indices I get passed for an interaction. And so for bonds, I already know that there will be an index array with 3 entries in it. And so since I already know that once I look up the parameters of the bond in a type table, this will have a distinct type. I can again use simple overload resolution to call the correct function that implements the right force law. And so this dispatch interaction here handles old bonds, and it avoids code duplication for loading indices and loading coordinates, computing coordinate distances. So that's already a step forward. But I can actually add further overloads to also handle angles. Since there I know that the index array will have 4 integers, I can add an overload. And one thing that all the angles have in common is that you need to compute the distances from the central atom to the atoms at the peripheries. And also for all angles, regardless of the functional format, I actually have to compute the actual angle between the three atoms. And then for the type specific part, that tells me whether the force depends linearly on the deviation of the angle from the equilibrium value. I can again use an overload to select between the different options. And thanks to these overloads, I actually need to implement a loop over all the interactions for a given type only a single time. So I can just generically now take an index table and the parameter table, some coordinates and some forces to write the output to, and loop over all the interactions there. And since I have these overloads in place, this works even for all the categories. This works for bonds, angles, and dihedrals. So now I need to implement that loop only a single time, whereas previously that had to be implemented 30 times for all the types individually. And now I'm still left with the task of handling all the different types. So I need to somehow be able to write a loop to say, so for all your types in the code, compute all the interactions. And now there's a problem. As I illustrated before, that bonded interaction data is now a tuple. And so I can't just write a for loop that, you know, iterates from 0 to number of elements in the tuple and then process one element by one element, because tuples can only be indexed and accessed with compile time constants. So unrolling this loop by hand and just calling it manually for every separate type is also not an option, since we don't want to repeat ourselves. And what we really need is something like for each tuple, where we can apply a function object to all the elements inside a tuple. And in the last part, I'm going to illustrate how that might be done. Since C++17, there's actually now a function called std_apply that we can use as the first step. And so what apply does is it simply takes a function and a tuple, and then the result is that the function g here will be called with all the elements of the tuple as arguments. And now this reduces the problem to finding a way to implement g in terms of the function f that we want to call on all the elements, and then apply that to all the arguments. So instead of receiving a tuple here, we've already simplified the problem to applying f for every argument in a template parameter pack. And we can't just say f args and then unpack, because we can't create a variadic number of statements just from a single expression. And we might try to dispose of the return values just with a helper function. Say we have this little function here, this dispose return value that takes an arbitrary number of parameters and then does nothing. this works in principle, but only if f returns has a non-void return value, because we cannot have void as the argument type of this little helper function here. And so now let me remind you that there's a thing called the comma operator. And A comma B means evaluate A, this card return value, then evaluate B and return the result of that. And so what we can do now is use that comma operator to apply F to the template parameter pack, discard the result, replace result with 0, and then unpack and pass to this both return value. And that actually works. The only thing is we don't actually need the helper function anymore, because if we have the comma expression that just returns zeros, we might as well put all those zeros, for instance, in an initializer list that then doesn't get used, but f nevertheless gets applied to all the arguments regardless. And so we're now able to use SCD apply together with this initializer list trick. And so we can implement the final for each tuple that we were looking for by saying that G should capture the function that we want to apply to each element and should take a variadic number of arguments. And then by constructing this initializer list as a side effect, F will get applied to all the elements. And then the only thing that we need to do is to apply G to our input tuple. And so if we now want to compute all types in our bonded force implementation, and if we also define this lambda intermediate function that computes just one type, here capturing the pointers for the coordinates and forces, then we don't have to manually unroll the loop anymore over the tuple. And instead, we can now just use this for each utility. And then that will get the compiler to unroll the loop for you and really compute all the types. And so we've now seen that a C, instead of a C union with it and replacing that with this and this thing C++ types, we were able to reduce that code duplication, and we were just able to have a single loop over all the interactions that's reused for all the types. And we just need one interaction dispatch per category, instead one dispatch for every type. And indeed, there's even more. So for instance, the force functions that calculate your force loss, they're now extracted of the call stack that loops through the interactions, and you could, for instance, use them in the TPU implementation too. And if you do it in this way, your code actually becomes really trivially extensible. If you want to add a new type, the only thing that you need to do is to define the type itself and add the force functional. And then you only need to add the type to one list. And that takes care of the rest. You don't need to implement a complete force loop that handles all the interactions. And that also opens actually new optimization opportunities. So we can, for instance, use that framework to generate new synthetic aggregate types. And the motivation for doing that is that the computations that I just showed you are heavily memory bound. So that means that it's much more expensive to load the coordinates and store back forces than to compare or than to compute the actual forces. And so if you're dealing with one angle, then the chances are that inside that angle, you're also dealing with two bonds. And then if you can combine or do the computation at the same time, so you load the three coordinates and you're computing the angle force, and then just immediately also compute the forces due to these two bonds, then you can improve the cache hit rate and get better performance. And having that type-aware framework available means that we can just make a new synthetic aggregate type where we store both the information of the bonds and the angle. Yes, and with that, I only want to add that here this presentation has been simplified a bit. For instance, I didn't take into account things like periodic boundary conditions. I also didn't talk about potential energies and free energies that you also want to compute normally in a molecular dynamics simulation. And that means that the amount of code duplication that you eliminate is actually bigger than what you might think just from the material here. Yeah, and with that, I'd like to end and thank you for your attention.